Cool. Okay, I'm gonna get started. Hi everyone, thank you for coming to my talk entitled From Parentheses to Perception, How Your Code Becomes Another's Reality. So a little bit about me. I am a senior front-end engineer at Slack. If you're not familiar with Slack, it is a chat-based collaboration tool. I'm also an organizer of Empire.js, which is an annual JavaScript conference that happens in New York City. We just had one last month. And I'm also an organizer of Brooklyn.js, which is a monthly JavaScript conference that happens in Brooklyn. So I know just how much work goes into putting on an event like this. So could we get a round of applause for everyone who helped put this together? Thanks for doing that for me. All right, so you can find my slides at that link, and feel free to tweet questions, comments, or compliments at my Twitter handle, Zeigenvector. I'll also be around in the hallway track if you have any questions after this talk. So to get started, we're going to go on a journey on how this code here, this HTML, CSS, and JavaScript, ends up going through the computer and ends up coming out the other side as a mental representation of your web application. So in this case, that lovely green send button. And also, how you know that that is a button that you can click and you figure that that's going to probably have some effect on the web page. So we're going to do this in 4 steps: parsing, rendering, perceiving, and comprehending. Just a little insight into how I see this. I see that there's kind of this symmetricality to this process. I see that rendering and perceiving are 2 sides of the same coin, and parsing and comprehending, so the computer and the human side of this, also have some symmetricality, there's some comparing and contrasting that you can do. So I just want you to be a little tuned to that, and maybe you can see some of the connections that I see in there. Also another caveat, right, like we made computers as humans, so we know all that there is to know about how computers work. I might not personally, but humankind generally knows how computers work. However, we have to do science to be able to figure out how humans work. Especially as you get more into the higher levels of perception and cognitive psychology and cognitive science, we're starting to get into more theories and hypotheses rather than facts that we know for sure. When we talk about like vision and the neuropsychology behind that, there's a little bit more concrete evidence going on there, but just a warning that cognitive science is pretty theoretical at this point still. So let's take the first step. So parsing. How does the browser process HTML, CSS, and JavaScript? So most programming languages have a vocabulary that is described by regular expressions and a syntax that is described by a context-free grammar. A context-free grammar means that there is a set of production rules that describe all of the possible strings in the language. In context-free grammars, these rules are simple replacements that can be applied regardless of context, hence context-free. For programming languages, these rules are all generally defined in a specification or spec. So in general, the parser's job is to take the document and break it down into a structure that the program, in this case, the browser, can use. And this process is going to be done based on the syntax rules of the language that the document was written in. The result of parsing is usually a tree of nodes that represent the structure of the document. And this is called a parse or a syntax tree. Parsing can be separated into 2 parts: lexical analysis and syntactic analysis. Lexical analysis is the process of breaking down the input into tokens. And tokens are the language vocabulary, the collection of valid building blocks for that language. And this process is done by what's called the lexer or tokenizer. Syntactic analysis is the process of applying the language's syntactic rules. What tokens can go next to what, in what order, etc. And this process is achieved by the parser. But curveball, HTML isn't context-free like a lot of other programming languages, and therefore can't be parsed by a regular, as in regular expressions parser. So this is because HTML is designed to be more forgiving of human error than other programming languages. In fact, the HTML spec requires that HTML be 100% fault tolerant. This is why you never see an HTML syntax error. It will always render something, even if it's not exactly what you were thinking. Thus, a lot of the parser's code goes into fixing HTML author mistakes, like invalid tags, unclosed tags, and incorrect nesting. And while it's really great that the parser will never error, it also means that browsers have to go and make these custom parsers. And browsers are like a million lines of C++, and a big chunk of that is dedicated to this parser. Luckily, CSS is a little bit easier. It is context-free. What this means is that we have the option, at least, of generating parsers for it by feeding programs the rules of the language. So, for example, there are two known parser generators that have been used to generate parsers for CSS, Flex for creating the lexer, and Bison for creating the parser. And each of these take input files and then export something that is able to be used. So both HTML and CSS parsers end up building the trees that I talked about, representing the language that it parsed. So a DOM tree is created from HTML, and a CSS DOM tree is created from the CSS. So you end up with structures like this. You can kind of see that code that I showed earlier, but now it has some friends and some context, so you can kind of see a tree instead of just a line of nodes. So JavaScript is also context-free and could use a regular parser, but browsers end up complicating things in order to do some much-needed optimization, because JavaScript really has to be fast for our modern web applications to behave the way that we want them to. So I happen to know a lot about V8 because that team has done a really good job about creating accessible content for someone like me who doesn't really know how this stuff works to understand. So I'm going to talk a lot about how V8 works, but I'm sure other browsers do things in similar ways. So V8 uses two parsers, an eager parser and a lazy parser, to eventually create two structures called an abstract syntax tree and a scope structure. So the eager parser is the full parser and is used to parse the functions for compilation. It builds an abstract syntax tree and scope functions and is able to find all of the syntax errors. Lucky you. The lazy parser is also called a pre-parser, and it skips over functions that shouldn't be compiled yet. It does not build an abstract syntax tree, but it does build scope structures, but it doesn't fully process them. And the lazy parser also finds only a limited set of errors. So the abstract syntax tree and the scope structures are then going to get fed into a baseline compiler. So in the case of V8, a bytecode generator is going to walk the AST and the scope structure and turn it into bytecode. This step could also return machine code or assembly, as V8 did in the past. This low-level code is then going to get executed by the interpreter. In the case of V8, this interpreter is called Ignition. And then the bytecode is going to get fed to an optimizer compiler, which recompiles functions that get used a lot and are worth speeding up. So in V8, there is only one optimizer compiler that is called Turbofan. And so because JavaScript has a just-in-time or JIT compiler, the code that is going to be compiled at runtime and information used from initial runs is going to get fed back into the compiler and is going to be used to speed up the function, assuming that the function will continue to handle cases like it has seen in the past. If you suddenly throw it something different, it can't use that extra information that it's gathered from previous runs, and it'll go back to the original parse. Okay, so we've parsed all the code, we made it into something that the browser can use, so how does the browser end up using it? And how does it end up deciding what pixels to put on the screen where and move them around? So the DOM tree and the CSS DOM tree that I talked about earlier are going to get combined to form a render tree. And the tree is going to get formed by traversing the DOM tree, and for each visible node, information from the CSS DOM is going to get applied and added to the render tree. So nodes that aren't visible and therefore won't get included in the render tree are tags like script tags or elements with display none. browser is then going to traverse the render tree to start off the layout or reflow stage. So it's going to traverse the render tree and calculate each node's position and size within the device's viewport. So in this phase, all of the relative measurements are going to get converted to exact pixel locations on the screen. Then the painting step is going to happen, in which the browser is going to take all of the laid out elements in the render tree and make layers from the bottom up in 12 phases, determining what color to paint each pixel. And the paint process is going to create a bitmap for each layer, and then these bitmaps are going to get sent to the GPU for compositing, or more technically, smushing all of the layers together. But websites these days are interactive. Users are going to click and drag things and scroll and type, and pieces will change, and the browser must update based on these interactions. So the browser is going to have the option to repaint every 60 times per second or every 16.6666 milliseconds. So then, what about JavaScript? JavaScript is single-threaded and is going to run on the browser's main thread along with all of the style, layout, and painting calculations. So everything that gets called in JavaScript is going to go onto the stack. Synchronous calls are going to go right onto the stack, and async callbacks, like those from web APIs, are going to end up getting thrown into a callback queue, and then are able to be moved to the stack by something called the event loop once the stack is cleared. So as I mentioned, all of the renders that we just talked about are trying to get done every 60 times per second. But renders can't happen if there's anything on the JavaScript call stack. And this is how jank happens. So if your JavaScript isn't all able to finish what it's doing in 16.66 milliseconds, you're going to end up not getting that render, and frames are going to get dropped. Okay, so then how does our brain take those beautiful pictures that the browser is creating for us and create an image of that in our minds? So how are we going to be able to know that that button that's getting created is green and white and is indeed a button? So what's going to happen is, in the case of a computer, the light is being emanated by the computer screen, and that light is going to go into our eye. In the case of the general world, light is going to get reflected off of objects in the natural world and go into our eye in a similar way. So the first step here is transduction, or converting information in the environment, in this case light, into neural signals. So that visible light is going to enter our eye and get reflected onto the retina with the help of the cornea and the lens. This image is going to get projected onto the eye upside down and backwards. So photoreceptors in the retina are going to turn this light into neural signals using cells called rods and cones. Rods are found primarily on the outside and the periphery of the retina and are used to see at low levels of light. And they have a relatively slow temporal resolution, so flickers above 15 times per second won't end up being detectable by then. Cones are found primarily in the center, or fovea, of the retina. And there are 3 types of cones that differ in the color of wavelength of light that they absorb. So there are blue, green, and red cones. And these are used, again, to primarily distinguish color and other features of the visual world at normal levels of light. They have a relatively high temporal resolution. So flickers above 60 hertz, or 60 times per second, are usually not going to be detectable by them. And this number might sound familiar from the rendering section, and I really doubt that this is a coincidence. So then the neural signals from the eye are going to get sent to via the optic nerve to the brain, and they're going to first end up at a structure called the optic chiasm. So the signals from both eyes are going to meet at this structure. They're going to be combined and split by visual field. So the right visual field is going to get sent to the left side of the brain, and the left visual field is going to get sent to the right side of the brain. So we're not talking about which eye's information gets sent where. Each eye has a right and left visual field, and they're going to get combined and sent to the requisite sides at this point. So then most of the signals coming off of the optic chiasm are going to get sent to structures in the brain called lateral geniculate nuclei. We have one on each side. And this information is going to collate and stratify information from different eyes. So each lateral geniculate nucleus has 6 layers, and I think it's really cool that they preserve the topography of the retina, with corresponding parts, like down through the layers, are going to correspond to a specific part in the visual field. So if you go down the 6 layers, layers 1 and 2 are going to get information about a specific part of your environment. The information is going to come from the rods about movement, depth, and small differences in brightness. Layers 3 through 6 are going to get information from the red and green cones about color and form, and the cells that get information from the blue cones are kind of in between the layers. Signals from the lateral geniculate nucleus are then going to get sent to the primary visual cortex, which is located in the occipital lobe. The correspondence between a specific location in the primary visual cortex and your subjective visual field is very precise. But there isn't a strict mapping of retinal area to area on the cortex. So in humans and other animals with a fovea, the cells there are really dense and compact compared to more peripheral areas within the retina, remember? So a large portion of the primary visual cortex is dedicated to that small central portion of the retina called the fovea. And this phenomenon is called cortical magnification. So cortical cells here, some of them are going to have a specific orientation of features in the world that they respond best to, and many also respond best when that edge is moving through their visual field that they are responsible for. There are also other cortical cells in the primary visual cortex that respond best to color. And then information from the primary visual cortex is going to get fed back into the lateral geniculate nucleus to help with ongoing discrimination and processing there. So you're going to get that top-down processing. You'll hear a little bit more about that as we talk about other things. So then these signals are going to get sent to higher visual processing centers that actually help us perceive what we're seeing. So visual perception doesn't stop at sight. And this is evidenced by people with what's called agnosia. So they have working visual systems, their eyes work fine, but they have trouble recognizing objects in the world. So to glean meaning from our surroundings, we need more processing, starting with pattern recognition. So we're going to start to figure out and use this visual information that we have to tell what is object and what is background, and distinguish objects from one another. So object detection relies on being able to tell the difference between light reflected off of an object and its surroundings. And remember, the neurons that we discussed at various stages are going to be really good at picking up these differences. So then we need to translate the data about different regions into data about different forms, such as color, size, and shape. So it might seem obvious here that the pixels down in the bottom right corner representing our new brain friend are indeed representing said brain friend. But to lower level visual systems, it's just data. Just like how when you render a specific element on the screen, it eventually just becomes a bunch of pixels surrounded by other different color pixels. We're kind of reversing that process, which I think is kind of neat. So then we're going to start to recognize and identify these objects. So once we can start to determine what is object and what is background, we can start to figure out what these objects actually are. So, and this, something that's really cool and is this cool high-level process is that this occurs even if we haven't seen that exact object or that object from that viewpoint before. So the popular theory is that object recognition depends on multiple stored representations of certain categories of objects. And we match objects in our world to those categories by seeing what most closely matches. So when you see this green rectangular thing with curved edges and this weird white text in the middle, you know that's a button because you've seen other buttons before, and you know that buttons are things that you can click on because you've learned what that is. What about all those cool animations from JavaScript? How do we perceive motion? We haven't really talked about that. So, you know, the browser is not creating a consistently moving thing. As we said, you get 60, maybe 60 frames per second. but that's not like natural motion like we're used to seeing. But our brains don't care. We see it as continuous motion, and this quirk is called apparent motion. And we think that it comes from the fact that we evolved to see things moving in a natural world, not frames on a screen that are theoretically flickering. So our brains have evolved to resolve these inconsistencies in ways that are consistent with objects moving through the natural world. Okay, so how do we know that those weird white pixels in the middle of that green curvy rectangle are words, right? So how do we know that, and how do we know that it says send in it? So how do we understand written language, and or how do we read? So to understand written language, we first have to recognize that those pixels on the screen are words. I think this is a similar process to how we recognize any other types of object. We know what words generally look like. But words and language in general get some special processing. So we process words as holistic units, not as separate letters, which I think is cool. And we recognize words faster than non-words, and this latter effect is called the word superiority effect. So we are also able to understand words when they are smushed together better than if they have spaces in arbitrary places. In fact, the impact on space removal is much greater in meaningless passages, suggesting that meaning is important when it comes to reading and even feeds top down when we're trying to parse things, which I think is kind of similar to how the optimizing compiler sends information back and uses that information for future parses. So to be able to assign words from the language to words that we see and even sounds that we hear, at this point, these processes are getting pretty similar. We must search around our mental representations of these words, so the way that we store these words in our minds, we have to search around for probable matches. The classic theory is that we have a mental dictionary and mental lexicons. We have discrete words stored in our brains, and then we go through and we activate several potential matches that might end up matching the word that we are seeing or hearing. And then as the context progresses, we see what ends up fitting in the context. And then at the end of the sentence, one winner emerges. So this whole process is kind of like the human lexer. We're talking about entire tokens. But some theories suggest that we don't store the entire word representations, but rather sub-symbolic processing units. So again, a lot of cognitive science is theoretical. So once we access the word, we have access to its meaning and syntactic and thematic rules. So then we can begin to parse the sentence and construct a representation of the sentence's meaning. So when we parse the sentence, kind of like what we discussed with programming languages, we're going to determine what syntactic category the word is in, and then combine those categories to form phrases. At this point, we start to construct a representation of the meaning of the sentence. Exactly, again, how we arrive at the correct meaning of the sentence is still an open question in psycholinguistics or human language processing. So a popular version here, I picked out two that I think were different enough and also interesting enough. One of the popular theories is called the garden path theory, which is that we construct the simplest parse first, and then we see if it makes sense once we start to integrate semantic information and context. And if not, then you have to end up going back and reparsing. So this explains sentences like, the horse raced past the barn fell. These are called garden path sentences because you are led down the garden path until the end when you realize you did it wrong. First time I heard this sentence, like the first 5 times I heard this sentence, I didn't get it. So here it is written out, and here is a hint. Yeah, not like usual language, which I think has a part to play in why we end up going down that garden path. So another theory that psycholinguistics have about how we parse sentences are constraint-based theories. So these appeal to this larger idea that has emerged in cognitive psychology, that the brain is a statistical reasoner. which I personally find as an engineer to be appealing, maybe because it's kind of similar to how machine learning works. So the idea here is that over time we develop a sense of the frequency and distribution of events, and then this ends up helping us to understand what was meant by a particular sentence with a particular parse, even if that sentence was ambiguous. And in fact, human language has a lot of ambiguity, both semantic, so in the individual word sense, and syntactic in the parsing of sentences. So human language has a lot of ambiguity, but we don't even really realize it because we're so good at finding the intended meaning of a word or sentence based on context and frequency. And this also is what makes puns possible, so ambiguity is pretty neat. Humans are also very good at forgiving syntax errors. So even though it's all really complicated and wishy-washy, generally going to understand what someone says if they mix two words up. If they're not a native English speaker, you can generally understand what someone means when they say a sentence to you. Something that's also worth mentioning about reading is that it's an automatic process for us. So if you had an email account in the 1990s, this might look familiar, but it's real science. It is called the Stroop task. And the idea here, if you're not familiar with it, is that you're supposed to say the color that the word is written in and not the word itself, which is funny because this is easy if you have full color vision. This is easy for adults who know how to read. And this is hard, though. And the idea here is that because reading is an automatic process, we have to actively suppress it in order to be able to bring up the not automatic process of color discrimination and being able to name the color. Okay, so we made it through our journey from parsing to rendering to perceiving to comprehending. I hope you saw some of the parallels that were in there. Here are some resources if you want to learn more, and here is the track list of all the songs that I butchered. Thank you.